At the University of Washington, a team of scientists are writing the software to identify and track any objects in the sky that change with time. They are working to build the largest census of our solar system ever undertaken. They work with groups like the B612 Foundation to see if any of the asteroids pose a threat to the Earth.
For centuries, people have created maps. Humans create maps to put themselves in the context of society. We do the same thing in astronomy. If we want to understand the position of the Earth in the context of the solar system, how it formed, how it evolved, possibly even where it will end up, what will its ultimate fate be, we want to create maps of the solar system to understand what are the populations of the planets, the dwarf planets, the asteroids and the comets, and to understand from these populations, from this census of our solar system, how our solar system and how the Earth came into being, how it formed and evolved. One of the first discoveries that was made using a telescope was way back in 1680 when a German astronomer named Gottfried Kirch discovered the Great Comet. Comet that was so bright that it was visible, at least it was said to be visible during the daylight. Since that time, we've used telescopes to try and map out the populations of asteroids within our solar system, continuously searching the skies to look for anything that's changed, anything that's brighter, anything that's moving. The human eye is remarkably good at identifying things that change on the sky. And it's been only in the last 30 years or so that we've had the technology and the algorithms and the software that allows us to compete with the human brain in detecting and identifying asteroids as they move across the sky. This is what we do at the University of Washington in the DIRAC Institute. We build machines to map out the skies, to create this census of our own solar system. We build algorithms that search through images. We identify anything that moves or changes on the sky. And we do this with algorithms that are smart enough that they work better than the human eye. And this allows us to produce our first systematic maps of our own solar system.
So why do we care about near-Earth asteroids? Well, the reason we care is that they occasionally impact. And when they do that with energies of thousands of nuclear bombs. In 1908, an object entered the atmosphere above Russia, above an area called Tunguska. This is the famous Tunguska event. So that object was fairly small. It was, we're talking about something like 40 meters in diameter. But what it did, it exploded in the atmosphere. The shock wave that it created leveled some 2,000 square kilometers of the forest beneath it. Now, we were really lucky at the time because no one lived there. So there are no confirmed casualties, from human casualties because of this object. But we may not be so lucky next time. Things like this have happened more recently. In 2013, in February, an object, a similar size, actually a little bit smaller, some 20 meters in diameter, exploded over a place called Chelyabinsk in Russia. It released enough energy to essentially smash the glass and damage roofs all across that town. About 100 people were hospitalized because of that, because of injuries sustained because of that event. And incredibly, we were again lucky because of the way this asteroid impacted the Earth. It exploded at very, very high altitude, some 30 kilometers above the ground. So by the time that shock wave reached the Earth, it was quite diluted. And relative to what could have been, the Chelyabinsk event was actually a disaster averted.
Something the size of the asteroid that hit Chelyabinsk, Russia, is kind of in the middle. And so this is something that would happen maybe every 100 to 200 years on average. But again, impacts are all based on probabilities. And so we never know for sure exactly how much time there will be between impacts for asteroids of the same size. Knowing how many objects there are of a given size will then tell us something about how often we expect an impact from an asteroid of that size to actually occur.
Now, we know that the Earth is not that lucky all the time. There's evidence for that in Arizona. There's a kilometer-sized crater remaining there that has been there for the last 50,000 years from an event that was quite similar actually to the Tunguska explosion, except that this object reached all the way through the atmosphere and impacted the Earth. We are now living in an age where we can actually find those objects and know whether something like that might happen, and we're actually living in an age where we can do something about it.
Large Synoptic Survey Telescope, or LSST, will have a major impact on our knowledge of asteroids and mapping the solar system. With this data, we'll discover about 10 times as many moving objects in solar system as we know today. So in total, we'll have over 5 million moving objects in our catalogs after 10 years of surveying.
LSST will find about 100,000 near-Earth asteroids, larger than about 30 meters, between 20 and 50 meters, depending on the albedo. Total, down to all sizes, because of course we'll find objects smaller than that as well, I expect we'll find more than 250,000 objects.
LSST construction project is entering its final phase. In about 2 years, we expect to get first images, and in about 2.5 years, we should start regular operations. We started a long time ago. The federal part of the construction started in 2014, but the project was in making since 2004. So some of us have been working almost 2 decades on the project. And finally, now we can even touch it. The building is almost done. We need to put some cladding on the dome. The rest of it is done. The primary tertiary mirror, which is the main optical element of the telescope, arrived to the mountain in May, and it will wait for about a year until telescope itself, or what we call telescope mount assembly, is fully transported from Spain, where it was assembled, tested, everything is fine with it. Now it's taken into smaller pieces, put in containers, shipped to Chile, and we expect to have it reassembled by the end of next year. And then we will test mirrors, collimate the whole telescope, and then we can add the camera that, by the way, will be the largest astronomical camera in the world. It will be about 3,200 megapixels in one single camera. It's not just about asteroids, it's also about a lot of other science, including cosmology, the expansion of the universe, growth of structure in the universe. It's about studying our own galaxy, Milky Way, about exploring time domain, looking at everything that changes on the sky to very faint levels. It is one data set that will serve all of the science programs. It's not that each of these programs will get a chunk of the time that LSST will have.
I predominantly work with ZTF, the Zwicky Transit Facility. It's a new extreme wide field telescope housed in Caltech. We work with their astrometric and photometric data, fitting light curves and to asteroids to determine their rotation periods.
So one of the nice things about ZTF is that we get to test how our pipelines, the pipelines we are developing to determine rotation periods, to pull out colors from sparse data where you don't have observations on the same night, all of these things, how they scale up with larger amounts of data. By understanding the rotation period of the objects, as well as their colors, we gain insights on what their physical characteristics are likely to be. So certain types of asteroids have certain types of colors, and by looking at the rotation periods, we can also get clues on whether they're rubble piles or monolithic rocks. We can also search for binaries this way too. And these are all important pieces of information if you're going to do a deflection or asteroid mitigation mission.
And with this influx of new data, astronomers have to look to new tools to be able to analyze that data, to draw science from this huge volume of data that's coming from these survey telescopes. And this means acquiring skills in statistics, in computer science, to continue building skills in astronomy and physics. And that really starts building this field not only as just a field of science, but also a field of data science.
So the LSST project is really one of the most ambitious projects in terms of data that we produce. And software, of course, is one of the backbones, because if you do not have software that can analyze whatever images you can take those images and put them on the wall, and they're going to look very pretty, but you cannot draw any science from them. So data and the software behind the data is really what we are craving and what we need in order to advance our science.
What does it take to find asteroids? What makes it challenging to find asteroids? What asteroid means in Greek is star-like. If you take an image of the sky, just a single image, and if you look at it, and if I ask you, where is the asteroid in that image, you would never be able to tell. To understand what is a tracklet, you need to know a little bit about how we find asteroids. You don't find an asteroid by just taking a single image in the sky and then saying, look, there's my asteroid. They all look like stars. What you do instead is you take an image, and then you come back to the same field in 20, 30 minutes later. What you're going to observe then, if you compare those two images, is that most of the stars are in the same place, but your asteroids have actually moved, so you can see it move. Those pairs of observations of the same asteroid, you can think of them as a little arrow in the sky that you can draw in the direction of asteroid's motion. That is what we call a tracklet. MOPS is an incredible piece of software. It works well. It is something that enables us today to find asteroids. But it's not the best we can do. You build this phenomenal, large, huge telescope to survey the entire sky, but 20 minutes after your first observation, you have to go back. So you cannot survey the entire sky in the same night because you have to go back to build tracklets to identify that this object has moved. So you have these incredible large telescopes that in effect can observe only half the sky that they otherwise could, because we don't have software that's good enough to, in essence, combine single observations from night to night to night. And this is something that we can do better.
What Professor Yersh and I started looking into is there a more natural or intuitive framework that we could shift to make the linking problem easier from not only that standpoint, but also from the standpoint of, allowing a telescope to choose how it wants to observe the night sky, but also still discover asteroids. And it's really in this kind of mindset that Thor was born. So every asteroid, anything that moves in the solar system has an orbit. It's essentially its path of motion through the sky and through space. And so the way that Thor works is, as opposed to building all the linkages that are allowed by your data, we just say, here's an orbit of something that moves in the solar system, a test orbit. Find me all the data, all the detections that could belong to that test orbit. Naively, what you could do is you could say, okay, we know of 800,000 asteroids, let's test out 800,000 orbits and see if we can discover all of them. Now, of course, testing orbits is still computationally expensive. That's never not been true. But we can make use of certain things that are true about asteroids, and one of those is they belong in families. Certain asteroids exhibit similar properties to other asteroids. And so you don't have to test 800,000 orbits to discover 800,000 objects. You maybe only have to test a few thousand. And that's kind of the power of Thor, is it's shifted the framework from build me all the linkages that my data allows to here's a linkage I want to test, find me all the data that supports that linkage. The good news is that Thor works, and it works really well to discover mammal asteroids. It's working really well to discover things that are further out in the solar system. We're now working on extending it to discover populations that are closer to us, so these are the near-Earth asteroids. But we hope with a couple more months to years of development that we can successfully discover all populations, or not be biased to discovering any population more than others. And if we can do that, that means we can allow telescopes which have solar system science in mind the liberty to choose their own cadence, the liberty to choose how they want to observe the night sky. And that's something that's super promising, and I am extremely excited about.
Planetary defense has two main components, two steps. The first step is to find potentially dangerous asteroid. And then if you establish that there is an object that eventually will collide with Earth, then you have to do something about it. You have to mitigate it.
So B612 Asteroid Institute is a unique place, and what makes it unique is that Ed and the group that have founded it found a way to bring together a very diverse group of people to build tools and build machinery that will allow us to discover asteroids, to understand how dangerous they are, and then ultimately to do something about it. Part of these teams are also postdocs who are here with us at the University of Washington. who use this machinery that the Asteroid Institute is developing to track asteroids through the solar system to understand actually whether those asteroids are going to impact, and if they do, what can we do, what do we need to do to move them off course.
The B612 Asteroid Institute ATOM project, ATOM stands for Asteroid Decision and Analysis Mapping Platform. ATOM is a piece of software that is being built in the Google Cloud. So it uses the Google Compute Engine to be able to do large-scale computations of looking at the asteroid impact threat from a theoretical side of things. The project that I'm currently working on with the B612 Asteroid Institute and the DIRAC Center is one to try to understand the distribution of deflection scenarios that we can use for trying to get asteroids to not hit the Earth. So here we're really trying to look at a big population of fake impacting asteroids. We have 10,000 of these asteroids that we're studying, and based on the orbits of these asteroids and how their orbits intersect the Earth, we are trying to look at how much of a push you would need to give these asteroids to get them to go around the Earth rather than hit the Earth. What we care about most when we're looking at the orbits of these asteroids and how they intersect the orbit of the Earth is that in order for an impact to occur, you need to have the orbit of the asteroid and the orbit of the Earth cross each other. But in order for the impact to actually happen, both the asteroid and the Earth have to be in the same place at the same time. And so it's looking at the geometry, we call it, of the orbit, as well as the timing of when the two bodies will be there that is the most important thing when we're talking about the impact of an asteroid and the Earth. The amount of time that we have before an impact is set to occur to have a spacecraft like a kinetic impactor travel to that asteroid and gently push it out of our way really plays a big part in how much we need to push that asteroid. So the farther in advance before the impact is supposed to occur that we're able to figure out that this asteroid is going to hit us at some point in the future, and that then allows us to send this spacecraft up to actually physically push the asteroid, the smaller the push will be that we need to give that asteroid. So the more time we have is always better. This method is only good if we have at least 10 years or more before an impact would be set to occur to get it to miss the Earth. Otherwise, we would have to come up with some other type of method to avoid that asteroid impact. So there is one new mission that is currently in the works that is going to help us start to actually try to figure out one piece of this whole puzzle of trying to get an asteroid to not hit us, and that is the DART mission.
So my involvement with the DART mission is actually a very interesting one. When people try to deflect asteroids, in order to make this very cost effective, they go and choose asteroids that are very close to the Earth because it's relatively inexpensive to send a spacecraft there. But it means also that they are close to the Earth and that they will remain close to the Earth. And if you change the trajectory of one of those objects, you better make sure that the asteroid is not going to become dangerous after your involvement. So my involvement with DART is exactly that. I am making sure that whatever DART does, however DART hits the asteroid, is not going to endanger humans by changing the orbit of the Didymos system in such a way that it would impact the Earth. Didymos, for instance, the target of the DART mission, is a potentially hazardous asteroid because it's close to the Earth. So you might want to make sure that for asteroids that are that close, you do hit them in the right way so as to avoid future impact. Blowing up asteroids is the first go-to idea that people have. Why can't we just nuke them or blow them out of the sky? But that has certain challenges. If we could fracture them into tiny little pieces that would actually burn up in the atmosphere, this would be viable. But the problem is that some of them are mountain-sized and others are actually made of metal, and making them break up into tiny little pieces that would actually burn up in the atmosphere is a very big challenge. And in fact, research has shown that if you try to just nuke them, then the largest fragments would still be large enough to enter the atmosphere, and you would have a shotgun blast instead of a single impact strike on the Earth. It may sound easy playing billiards in space, but it is actually not. Since when you impact the asteroid, there's lots of debris coming off the asteroid, and this actually causes additional momentum transfer. So you do not know a priori how much you're going to change the asteroid unless you have very precise models of how to do that. And this is exactly what the DART mission is going to tell us.
So the OSIRIS-REx and the Hayabusa 2 missions are both missions that are going to be returning samples of asteroids back to the Earth. And those samples are actually going to tell us things about the composition of these asteroids, so what they're made of, how rocky they are, whether they have water in them, and most importantly, how dense those asteroids are. This is really important information to know in general, so that if we discover an asteroid in the future that is going to be hitting the Earth, we would need to know very specifically as much information about that asteroid as we could to be able to know exactly what we need to do to try to get it to miss the Earth.
We talk about asteroids a lot from the point of view of planetary defense because some of them are a threat, and it's an important problem to understand and to do something about if there is one coming towards us. But I think it's important to understand that that's not all asteroids are. Asteroids are remnants from the formation and evolution of the solar system. You can think of them as breadcrumbs left throughout the solar system that tell us where the planets formed, how they moved, how will they move going forward in the evolution of the solar system. They might tell us things like, how many planets were there initially? Was there another Earth in the solar system that got ejected? Were there more planets like Jupiter that got ejected? Are there still planets that are out there in the solar system that we don't know about? So there are all these tremendous questions in addition to the planetary defense problems that we're trying to understand.
If we look towards the outer parts of our solar system, about 3 billion miles or 30 astronomical units away from the Earth, we find a population of asteroids which are called the Transnet Union objects. Transnet Union objects, or TNOs. TNOs are the remnants of the formation of our solar system. Even though we think we know an enormous amount about our solar system and the populations of asteroids that it contains, I mean, we're sending spacecraft out to the planets or the dwarf planets in the outer parts of our solar system, like the New Horizons mission that took those beautiful pictures of dwarf planet Pluto.
So recently we published a paper using our KVMod software, the software that searches for these faint moving objects, and in it we detailed the discovery of 39 new Kuiper Belt objects. So Kuiper Belt objects are relatively slow-moving and relatively large objects that are beyond the orbit of Neptune, from about 40 astronomical units to about 80 astronomical units. And the most famous of these objects is, of course, Pluto, which is now known to be only a single sample of a much larger class of objects.
With new techniques, we can get new results from old data. And something we showed with our first paper was we took some data that had been originally used to look for supernova, and we went back through that data with our asteroid searching algorithm, and we found asteroids in the same data. So our work here is about finding very faint asteroids. So we're trying to use the light from stacks of images of the same part of the sky to find objects that you wouldn't be able to detect in a single image. What we're doing is we're tracing the possible trajectories of asteroids as they go through kind of the same field of sky over multiple nights, and then we're kind of adding up the light along that trajectory. If you looked in a single image, you wouldn't find them because they'd be too faint. And when you add up the light along that trajectory, you can get a boosted signal from all the light from that asteroid in the different images and find fainter asteroids than you would in a single image.
So I had a recent paper looking at cratering in the outer solar system. There were actually a couple papers. The first one was looking at craters on Pluto and its large moon Charon. And the other one was looking at cratering on a much smaller Kuiper Belt object called 2014 MU69. All three of these objects were flyby targets for the New Horizons spacecraft. The spacecraft imaged Pluto and Charon back in the summer of 2015, and it imaged the smaller Kuiper Belt object on January 1st of this year. So we were trying to look at how objects, asteroids, out in the Kuiper Belt, which is a belt of objects out in the outer solar system, very close to where Pluto is located, how they impact and thus crater the surfaces of these bodies.
Oumuamua, our first interstellar visitor, an asteroid that originated outside of our own solar system, that was first observed by a small telescope on Haleakala, the mountain on the island of Maui, a small telescope called the Pan-STARRS telescope that observed this object that was moving across the sky. And once we'd actually determined its orbit, we could show that this asteroid didn't originate from within our own solar system, it was just passing through.
It was the first of its kind, first object that we've ever really seen outside of our own solar system, which was very exciting. And so being able to see that and interact with that was a new experience for most astronomers, and so it caused a lot of new exciting research, at least in the planetary sciences. When we are observing an object in space, we're not typically able to physically discern the entire object. A lot of times we're mostly just able to see the amount of light that it's reflecting. And so the amount of light it reflects is a lot of times dependent on the surface texture of the object and the surface shape. And so if an object, is completely spherical, you'd expect it to emit the same amount of light at all times. Whereas if it's elongated and spinning towards us or tumbling towards us in an interesting way, the amount of light it's reflecting from the sun is going to vary drastically.
So this variation in this light, the variation in the series of observations or the brightness of this object as we observe it multiple times over, how that varies tells us how fast the asteroid is rotating, tells us the shape of the asteroid, tells us whether it's fast enough that the asteroid has to be a single solid body, or maybe it could be made up just as a pile of rubble.
So it's interesting to think how astronomy has evolved over the years. I mean, we're talking about one of the earliest areas of science in human history. There are astronomers going back to 2,000 years ago in ancient Greece. And what we think of as astronomy today is people looking through telescopes. My students and I were just visiting the Lowell Observatory, the observatory where Pluto was discovered. And we were looking at the telescope that was used to discover Pluto that had these huge areas for photographic plates. So what Clyde Tombaugh would do, he would come there in the evening, he would put photographic plates on that telescope, he would expose them to the sky, and then would take them, develop them, and only days or weeks later would he actually see what he got. And that's actually how Pluto was discovered. He noticed Pluto only, I think, about 2 weeks after he actually took the image.
So I think the general vision that people have about astronomy is that we look into the skies and we enjoy the beautiful night skies and maybe count stars. But of course, astronomy is a little less romantic, if you want, nowadays, because we mostly look into our computer screens and the telescopes do all the watching work.
So the sensors that detect light, CCDs, they changed enormously. They appeared only 20, 30 years ago in commercial environment. And the key thing about using CCDs compared to the old technology of photographic plates is that they essentially capture all the light that comes in, while photographic plates capture only a few %. So all the telescopes in the world that switched to these new types of cameras, they became 10 times bigger overnight, just by switch to new technology. So that was a revolution. So we could see much fainter objects than before. At the same time, the development of computers, of data storage, of data processing tools enabled us to get lots of data and process it and then make it available in an easy way to everyone who wanted to use it.
Cloud computing is becoming critical because we're sharing data more than ever before. So we want all our data to be open source, all our methods to be open source. People can use our data and use our tools easily to reproduce our results and then to do their own work with the same data and learn new things.
Almost all astronomical observations are now digital, based on CCDs, and they require a lot of data processing and very sophisticated data analysis tools. And because of this change driven by technology, humans, astronomers, also are changing. Modern astronomers are now more and more computer scientists, statisticians, data users, software experts, not all of us, but many astronomers, much larger fraction than it used to be 20 years ago. And so this traditional division to theoreticians and observers is now rapidly changing to astronomers who are data savvy and those who are more hardware oriented, who are instrumentalists. And then of course, even theoreticians are changing. They're not working with yellow notepads anymore. They're writing sophisticated computer programs on very, very large computers and producing simulated universes or simulated objects.
I think personally that this is even more exciting, because if you look at the stars, they are beautiful, but you really don't understand much. But with all the telescope involvement that we have, we can not only look at stars or at the asteroids with a visible light, that's what we see with our eyes, but we can look at it in all sorts of different wavelengths, all sorts of different spectra, and that carries so much information. In fact, what motivates me and what I find amazing is that with so little light, with so little information, the amount of knowledge and the amount of science we can extract is really incomprehensible.
There are about, of the order, as I said, 30,000 dangerous asteroids that are larger than of the other 100 meters. But there are more than 5 million asteroids that LSST will discover. And for each of those, we will get beautiful light curves, multicolor light curves, because each will have about 200 observations over the survey period of 10 years. So it will be an enormous jump in data quality and data quantity for studying asteroids. It will become a very vigorous field. Many more people will study them because there will be this new, enormous, rich data set that will teach us many secrets of the formation and evolution of our solar system.
LSST will start operations in 2022 and then operate for 10 years. But if any of this interests you and you want to start tackling science questions now, there's a survey telescope operating called the Zwicky Transient Facility. And the data that they're releasing, their ZTF alerts, are in the same format that LSST will release. And so if you really can't wait to get your hands on LSST data, you should visit the ZTF website and you can download nightly alerts. And these alerts contain the detections of asteroids and things that have moved in the solar system. And so if you really, really want to try discovering asteroids, or you want to learn something about them, or if you want to ask a question that we have forgotten to ask of our data, I would encourage you to visit the website, download these alerts, and start doing some science.